Hey guys, welcome to the ninth episode of the AI series. In today's video, we are going to take a look at what are cost functions. So let's get straight into it. In the supervised learning video, I mentioned a single number called as the loss, the total wrongness a model tries to shrink. And we promised that we would try to make it concrete. And this applies for regression. Let's say we have a line and a pile of residuals, the difference between y hat and the actual value of y. And of course, we want one honest score that says exactly how this line fits. Let's build that score from scratch because the small choices we make right now will affect our algorithm later. Now, the first instinct is that we'll just add up all the residuals to get the error or the loss, which is the total gap, and done. But it's actually wrong. Residuals above the line are positive, residuals below are negative, and when you add them, positive negative, they cancel out. And a generally terrible line, missing wildly in both directions, could sum to a proud lying zero. So plain addition is out. We need a score where every mistake counts as a positive amount. No cancelling and no negative. This is where a special fix comes in, and it's genuinely beautiful. Let's say we square each residual. Squaring does two jobs at once. It instantly destroys negative sign and everything becomes positive, and it punishes big errors or big residuals far more harshly than small ones. But here's a picture worth 1,000 formulas. A square residual isn't just a number, it's literally a square drawn right on the gap, with the gap as its side. So the cost becomes something you can see. The total area of all these squares, watch as I tell the line, the squares swell and shrink in real time. And we're hunting for the line that leaves the least total area behind. Average those squared areas over all your points, and you've arrived at the most famous cost in machine learning, the mean square error. And this is the loss from the supervised learning video. And now it's completely concrete. And let me make it a little easier for you, because once you understand it, you own it for every point. Take the true minus value and minus the prediction. Then square the gap and add them all up and divide by how many points there are. The whole sentence is one formula, and it's the number gradient descent is about to go hunting for. A sharp viewer should be thinking right now, squaring isn't the only way to kill the sign. We could just take the absolute value of each residual and that'll be positive too. And it's even more simpler. So why does almost everyone want to reach out to square the number? And there are two reasons for that. First, the squared cost is smooth everywhere. Since it's squared, it results in a bowl or a parabola. And that smoothness is exactly what the optimization method in the next video needs to find its way downhill. The absolute version has a sharp kink at zero that makes the journey trickier. Second, squaring deliberately makes large errors even more painful. One big miss dominates the score, which is great when big mistakes are genuinely the worst. When your data has wild outliers that you'd rather not let hijack the whole model. There's even a bigger compromise called the Huber loss that behaves like squares for small errors and like absolute value for larger ones. So the choice of cost isn't a detail, it's a statement about which mistakes you care about the most. Now, the conceptual jump that ties the module together. The data is fixed, but we cannot change a single house. The only things we can move are the knobs, which are W and B, which means the cost is really a function of W or B. So let's plot it, not over the data, but over the parameters themselves. Sweep the slope from too flat through just right to too steep, and the cost traces out a smooth parabola, with exactly one lowest point being the intercept back as the second knob, which is B. And that bowl becomes a three-dimensional surface with a single point at the bottom. And that bottom is the best possible line for our data. So the entire problem of linear regression has quietly transformed into one sharp question. How do we find the bottom of this parabola? And that question has a very important answer, and that is known as gradient descent. And we'll be covering that in the next video.